So thank you everybody for coming. Welcome. So I'm very pleased to introduce Christophe Petit. He's been a frequent visitor to our group and worked together on isogeny-based crypto problems for many years. We're very pleased to have him back. He's been a research fellow at Oxford University most recently, and now a lecturer at University of Birmingham. So thank you, Christophe.
And thanks, Christine. It's a great pleasure to be here, and thank you very much for inviting me. So you may have heard of it. There's something called quantum computers, and that will break all our crypto today. So you want to do something about it, and maybe you want to find some problems that are not just discrete log and factoring that will resist quantum computers. And one of the problems that has been suggested recently is, family of problems is what's called isogeny problems. So they were proposed recently for, it wasn't, for post-quantum crypto and in other contexts. The reason for that, one reason for that is that at the moment, the best classical and quantum algorithms still require exponential time, so that's good. One reason I like those problems is because they're not just made for being able to prove the security of a crypto system, but they actually have some history. So David Cole, back then in 1996, already studied some of them. So it does give some more confidence than if the problem was kind of built up for proving your crypto system. And the problems are kind of natural from a number theory point of view, at least some of them. It's kind of natural. We'll come to that, but when you're given an elliptic curve to ask questions such as endomorphism ring, we'll come to that. Okay, here's the outline, given the motivation, hopefully. I want to kind of do an overview and then go to some recent results that maybe will excite more the people that know already about the topic. So I'll talk about the different protocols that exist in this area. I'll talk about what sort of problems are hard and easy, what sort of problem are easy and what sort of problem may be hard, let's say. And then I will go into this recent result of mine. Okay. All right. So let's start with isogenies and crypto protocols. An isogeny. So let P be a prime. So up to isomorphism, any supersingular elliptic curve can be defined over FP square. An isogeny is just a morphism, non-trivial morphism, sending one curve to another and preserving the neutral element. So it's a rational map, so you can write it as, if in Weierstrass coordinate, you could write it in this way, in terms of coordinates of E0. You get the images of phi of xy here. Just a bit of more of introduction. The degree is degree of this guy or the degree of this guy. And some notation will write E1 quotiented by, we'll write E0 quotiented by G equal to E1, when G is the kernel of phi. Okay? A little more of context. Am I here already? Okay. So isogeny problems. So all the problems that we interested in this area are about computing some isogenies, whatever this means, okay? Or some variants of this problem. For those problems to be hard, the isogenies must have large degree. So if the degree is small, you can just do exhaustive search. However, the kind of representation I show you here, if the degree is large, that's just not efficient. Okay, so we'll need some kind of trick to actually even just return the output in some efficient way. So one such trick is that if the degree is smooth, then you can write the isogeny as a composition of low degree isogenies, and that makes the representation efficient. Okay. In some protocols, and we'll come back to that, the attacker doesn't just get two curves and has to compute an isogeny between them, but he also gets some additional information. And at the end of the talk, we'll see how this could potentially affect the security. All right? Well, feel free to interrupt. I forgot to mention. Some more basic introduction. So over the algebraic closure, the L torsion is just isomorphic to ZL cross ZL, and each of those, and there are L plus 1 subgroups in there, and each of them correspond to to the kernel of a degree L isogeny when L is prime. Okay, so we can build this graph where every vertex is essentially a supersingular curve or invariant, and you have an edge between two curves if they're connected to some degree L isogeny. Okay, so those graphs are very cool. They're undirected, so for every isogeny you have what's called its dual, which goes in the opposite direction. So in supersingular case, everything is defined over fp square, or can be defined over fp square. The graphs are known to be Ramanujan. That essentially means optimal expansion. So if you do a random walk, you quickly reach uniform distribution there. If you think of the isogeny problems that are just computing isogeny between two curves, in terms of graphs, this would just mean computing path into those graphs. Okay, so maybe it's useful to have this intuition to understand what we're talking about. All right, any questions so far? Okay, let's go to the constructions then. A hash function, I would expect everybody knows what it is. So you're interested in collision resistance, pre-image resistance, and second pre-image resistance. First one meaning you cannot find two messages that hash to the same value. Pre-image resistance essentially means you cannot invert, and second pre-image is something a bit in between, perhaps, where you're given a message and have to find a second message hashing to the same value. They're, of course, a fundamental building block in crypto used for integrity, authentication, etc., etc. And the first protocol, well, the first construction based on isogeny in the supersingular case was Christian's hash function. So this is a supersingular isogeny graph, right? So the vertices are just J invariants, supersingular invariants, and the idea is that you split your messages, you message into bits, and each bit determines a step in the graph. So let's say you start here, and then if your bit is 1, you would go there, and if it's 0, you go there, etc., and so on and so on. Remember, the graph is regular, so at every vertex you have, well, in this case you have 3 vertices, but you also don't want to backtrack because that would give you a trivial collision, right? So the output of the hash function is just the final vertex that you reach here. So this chain invariant, okay? So if you want to solve for the pre-image resistance problem in this case, well, trivially what it means is that you're given 2 curves and you want to find a path between them, right? So you want to compute an isogeny, in this case of degree L to something that connects this curve and this curve. Another way to break the function would be to find a loop, right? Because that would give you a sequence of messages that together go back to the same message, and then you can concatenate this sequence of message with this message, and then you get a collision as well. So this would be an endomorphism in the elliptic curve setting. Okay. So the function is kind of nice. You can trivially translate the security properties in terms of isogeny problems. You also have this expansion property that means that translates into the fact that as long as the messages are long enough, the output will be uniformly distributed, which is also something that you would like for a hash function. Okay. All right. Any questions so far on the key exchange? On the hash function? No. Right. A second protocol I want to mention is a key agreement. So here the goal is for Alice and Bob to agree on some common shared key, while only exchanging public messages. Okay, so it's kind of well, for you it would be trivial, but for some audiences it's not intuitive that this is even possible. So Eve sees all the messages that are public, and then at the end of this conversation, Alice and Bob have a secret that should remain secret to Eve. And of course, there is a very standard way of doing that. It's called the Diffie-Hellman protocol. You choose a cyclic group, you choose a generator for this group, and then Alice will just pick a random A and send G to the A. Bob does the same thing, random B, G to the B. Then Alice takes G to the B, raise it to the A, this gives G to the AB, and Bob do something similar, and then they both have G to the AB. And if you believe that discrete log is hard, and actually Diffie-Hellman is hard, then well, decision in Diffie-Hellman is hard, then Eve can see all messages and still is not able to infer anything about the shared key. Great. So a very nice protocol based on isogeny was developed around those ideas. So here's what you do. So pick a prime P and two integers NA and B such that they coprime to each other. So GCD is 1. Pick a supersingular curve over FP square. Then what Alice does, like the equivalent of choosing a random A, is in this case, it's choosing a cyclic subgroup in the NA torsion. Okay, and then she computes the isogeny whose kernel is equal to this cyclic subgroup GA. Okay, so she computes this isogeny and the curve here. And so this gives a curve EA that she sends to Bob. Okay, Bob does something similar, except that he works with NB. So he chooses a cyclic subgroup GB within this NB torsion, computes the curve EB, and sends EB to Alice. Okay, and now you want the shared key to be equal to E0 quotiented by GA-GB, like the group generated by those two. Okay, so you can rewrite this as EB quotiented by phi B of GA or as EA quotiented by phi A of GB. Great, except that what is sent is this and this. So if you want to, if Bob wants to compute the shared key, Bob knows phi B, but he doesn't know GA. That's the secret of Alice. He knows GB, but he doesn't know phi A again. Okay, and similarly for Alice. So as such, Alice and Bob are not able to compute this shared key. So the key trick in Jao-de Feo protocol was to send additional information. Okay, so what they do is that well, this cyclic subgroup that Alice chooses can be represented as the subgroup generated by a point of this form. Okay, so if you take PAQA, a basis for the NA torsion, then you can choose alpha A and beta A, not both, at least one coprime to NA, and this will be a cyclic subgroup of order NA, right? So that defines the GA, and then if Bob reveals phi B of PA and phi B of QA, and now this is public information, right? Only alpha A and beta A are not public. So if Bob reveals this, then Alice can actually compute the image of this group through phi B. Okay? So that's the kind of trick that they use. I think it's very clever. Okay, a couple of additional comments. For this to be, so this works, but to be efficient, you would like NA to be smooth, because then the isogenies can be represented as a sequence of small degree isogenies, right? So this is important. And then you have to work with entorsions here, right? So you'd like this entorsion to be also representable in an efficient way in your computer. And there are two ways to do that I know. This is the way that Jao and De Feo suggested. So if you take NA dividing P minus 1, then the whole torsion will be defined over FP square. And that's great, okay? Because then you can represent everything over FP square. Another way to do that, and I'll come back to it, is to choose NA a pure smooth number, in the sense that if you write it as a product of prime, the largest perf prime is small enough, okay? If you do this, then essentially the torsion, you can represent any element in torsion as a sequence of elements in the Li to the EI torsion, and that makes an efficient representation as well. Not as efficient perhaps, but it would be putting more time as well. Any question on this? All right, so here's the key exchange. So the blue information is known only to Alice, the red information is known to Bob, and this is the shared key, right? So Alice chooses RA, and then Bob sends this, and from there Alice can compute this. So as I say, Jao-de Feo choose NA dividing P minus 1, but they also chose NI equal to per small prime, in fact 2 and 3, such that this is as efficient as possible. But if you want it to be safer, in my opinion, a priori, you'd like to choose the other variant with ni equal to p squared, roughly. So the reason for that is that, well, first of all, in their parameter, you choose very special primes, and that in crypto has a history of being a bad idea. And second of all, the degree here is kind of too small. So if you think of the two curves here in the graph, they're kind of closer than two random curves would be. And that potentially could lead to an attack. And in fact, the best attacks are better in this case than for generic isogeny problems. So for those two reasons, it could be a priori safer to use the other variant where you choose ni to be a product of small power of primes. Okay, any questions so far? But of course, I mean, this is more efficient, or is expected to be more efficient. All right, any question on the key exchange? No, this is all familiar to you. ID protocol, or proof of knowledge. Here the goal is that somebody wants to prove knowledge of a secret. So the prover wants to prove knowledge of some secret to a verifier without revealing anything about the secret. So that can be used, for example, in an authentication protocol. And the security requirements for those protocols are correctness, soundness, and zero knowledge. Correctness just means that if you know the secret, you should be able to prove that you know the secret. Soundness means that if you don't know the secret, you shouldn't be able to prove that you know the secret. And zero knowledge means that nothing is leaked about a secret. All right? And so typically those protocols are interactive and can be made non-interactive using some standard tricks. So here's their suggestion. The secret here is an isogeny between two curves, E0 and E1. The protocol is interactive. It's a 3-round protocol. So the prover will first compute those isogenies here. And that's like in the key exchange protocol. This isogeny will correspond to this, and like in the key exchange protocol, really, except that the picture is kind of turn a little bit. So the prover will commit with those two curves. The verifier will challenge the prover with 1 bit, so either 0 or 1. If it's 0, the prover has to answer with this isogeny and this isogeny. If B is 1, it has to answer with this one, right? So this is correct because obviously if you know the secret, you can compute this. This is sound because if you can answer to both challenges, so in both cases, when B is equal to 0 and B equal to 1, then it means that you know those 3 isogenies, and from there you can recover this one. And this is zero knowledge if you want to assume some special ad hoc hardness assumption. Okay, so I won't come to that. But okay, so that's another protocol, which is also kind of cool. And then, well, it's well known in crypto that if you have key exchange a la Diffie-Hellman, then you can derive public key encryption a la El-Gamal. Okay, so this can be done here. So you derive public key encryption from the key exchange, and that's kind of an exercise from a crypto background. And then we're also interested in signatures, and it's also well known that if you have an ID protocol, you can derive a signature out of it, right? This is called the Fiat-Chemie transform. If you care about post-quantum security, as I guess you would in this area, then there's an alternative called the Unruh transform, which does the job. All right, so in this paper that's available on ePrint, what we do with Stephen Galbraith and a student at Oxford is building an alternative protocol that has kind of stronger security guarantees than this signature, than this ID protocol, and we derive a signature scheme from there. Anyway, any questions so far? So that's about all in terms of protocols. There are a few protocols that were suggested that, like weird versions of signatures, etc. But I think those are the most interesting ones. Okay, so let's go to the math, the problems. Okay, that's an easy problem. So if you're given a kernel computing the isogeny, it's easy-ish. Let's see why. So given this kernel, there's something called Velu's formula. It's actually a very explicit formula that gives you a formula for the isogeny given the kernel G, right? So here xp just means the p, the x coordinate of the point p, and of course xp plus q means something similar, etc. So that's fine. That's an explicit formula, but as you can see, the efficiency here is at least O of size of G, right? So if G is big, this is not going to be efficient. And remember, in crypto, we want G to be big. We want the degree to be big. Okay. Well, if G is composite, as I already mentioned, you can kind of use a Chinese remainder theorem kind of representation and represent this G as a product of cyclic subgroup of order Li to the EI, and this makes it more efficient. And you can write the isogeny as a composition of small degree isogenies, which then becomes efficiently representable. So that's a problem that's easy, essentially. Here's a hard problem, on the other hand. So you're given a curve, E, and you want to compute its endomorphism ring. To the best of my knowledge, this is still hard, and this is the problem you would ideally like your crypto system to rely on. Since it's the hardest problem in this area. We focus on the supersingular case, so the maximal order is, the endomorphism ring is maximal order in BP infinity. The Quaternion algebra are ramified at P and infinity. And what I mean by this, this is a bit tricky to define properly, but essentially you can return this as this is a ring, so rank 4 ring, so you can just return a basis, so 4 elements, and each of those elements are endomorphism, so they're high degree maps, but you have to return it as in kind of an efficient way, as we already discussed. Okay. Nice thing about this problem is that it has some history, as I mentioned. David Cole, back then in 1996, already studied it. And the best algorithm he could come out with is exponential time. And that's essentially still the best algorithm today. Okay, so here's this. Any questions so far? No. Here's Coyle's algorithm, more or less. So suppose that you want to find an endomorphism for this curve. You fix a small prime, then you look at all neighbors, then you look at all neighbors of neighbors, and all neighbors of neighbors of neighbors. So you're building this tree. At some point, you'll find a collision. So you're computing all the J-invariants. At some point, there will be 2 J-invariants that are equal. And you can actually bound that based on the known bounds on the diameter of those graphs. Or you can expect that actually in square root of P, you'll get a collision. Okay, so that's a very simple algorithm. When you get a collision, actually you can suppose this vertex and this vertex are equal, but well, you just take this path and then you come back here, and that makes an endomorphism. And if you repeat that several times, say 4 times or a bit more, you get a subring of the endomorphism ring that you could reasonably expect to be actually the whole ring. All right, so this is nice, but not efficient, of course. Square root of P is exponential in log P. Another problem in this area is you're given 2 curves now, E0 and E1, and you want to compute an isogeny between them. Okay, so it's kind of similar to the previous one, except that in the previous one, E1 and E0 are equal. Right? Again, for this problem to be hard, degree must be large, so you cannot really return phi as a rational map. We mentioned that. This problem is the same kind of hardness as the previous one. We actually writing a paper on trying to make that claim formal, but it's not too hard to prove, at least heuristically. And in crypto, sometimes you see some additional condition on the degree. So obviously you want this to be this isogeny to be easily representable. So perhaps you'll require degree of phi to be equal to L to the E. So that's also the case in Christian's hash function. That doesn't really change the hardness, the complexity of the problem. The problem can be solved in about the same complexity, square root of P. So given the 2 curve, E0 and E1, now what you do, you build 2 trees from E0 and E1 until you get a collision. So essentially the same algorithm, and you expect to get this collision in roughly this time. Okay, so roughly the same problem, same complexity. Any questions so far? Great. I want to mention this during correspondence. So back then in 1931, Turing proved that there is a bijection between supersingular elliptic curves over p square up to Galois conjugacy, and maximal orders in the quaternion algebra BP infinity up to conjugation by invertible elements. And the correspondence is actually very simple. You just map E to its endomorphism ring. Okay, so essentially what this says is that every supersingular elliptic curve has an endomorphism ring that is maximal order, and they're in bijection. All right, under this correspondence, you can translate isogenies from E1 to E2 into an ideal from the corresponding O1 and O2, which is both a left ideal of O1 and a right ideal of O2. And the degree of phi will become the norm of I. I mean, there's this kind of dictionary that is clear from a mathematical point of view, but not very explicit and maybe not efficient to compute. And of course, we're working on that. Another interesting, relevant result in this area, I shouldn't say interesting because it's my result, but relevant, say, is what has been called the Quaternion isogeny problem. So it's in light of this correspondence between Quaternion and elliptic curves, one strategy that we tried with Kristin back then, 2009 already, I think, is to try to translate the hard problems for her hash function into problems for the Quaternion algebra, solve them in the Quaternion algebra, and then translate the solution back to elliptic curves. And with respect to this strategy, it was natural to consider this problem, which is kind of the equivalent of isogeny problems, but for the Quaternion algebra. Okay, so to be clear, we're given two maximal orders, and the goal is to find an ideal that connects the two of them, which has a norm, in the case of the hash function, wanted L to the E norm. Okay, so it's not too hard to compute an ideal that connects O0 and O1, but then the trick was actually to compute another ideal in the same class that had the appropriate norm. And this is solved in our Hans paper, Hans 2014, where we provide a heuristic algorithm that solves this problem with norm roughly equal to p to the 7/2. All right. Good. I'm nearly done with this kind of introduction, but yeah, sorry.
So here you solve the equivalent problem in the Quaternion algebra.
Yes. Yeah.
So, could you comment on what the problem is of translating it back to the
elliptic curve? Yeah, it's this one. So you're given two curves, and you want to compute an isogeny.
So, you solved it in
Quaternion, yeah.
world.
So in terms of translating back, if we could really solve that, we would solve everything in this area. But we do have a partial translation in some subcase that leads to a collision attack on Kristin's hash function for special parameters.
But is there an intuition why it doesn't seem to work completely, the translation?
Well, first of all, it's hard to compute the endomorphism ring.
So that's kind of the point, is he's stating it almost as an equivalent problem, which is the hardness of computing the endomorphism rings.
Yeah.
That's really the fundamental problem.
Yeah.
Okay.
So the translation back is kind of really the hard problem, actually. Okay. Right. I mentioned this during correspondence, and here I want to just rephrase what Kristin just said. So indeed, if you're given a J-invariant computing the corresponding order, so computing this correspondence is the hard problem. So that's something that you would hope for crypto that is hard, because otherwise everything is broken in this area. Okay. On the other hand, if you're given a maximal order, computing the J-invariant is something that you could call it the inverse endomorphism ring computation problem, and that's something for which we now have a heuristic polynomial time algorithm, And I say, no, actually, you should say, maybe we have had for 6 years, but hopefully this month the paper will finally become public. So that's kind of easy. So what you see here is kind of a one-way function based on this Düring correspondence, where in one direction you can actually compute the Düring correspondence, in the other direction is still hard and candidate hard problem for crypto.
If you have a factoring oracle,
No, that doesn't help. It doesn't help at all, as far as I know. And I think this is my last slide in this section. So I mentioned some problems that I think are hard. Here's the problem that happens that occurs in the key exchange and encryption and zero-knowledge protocol by Jao-de Feo. So you do have an isogeny problem where you given you're given two J invariants essentially, or two curves, and you want to compute an isogeny between them. But first of all, because you want the torsion to be defined over fp squared, you require n1 and n2 to divide p. Okay, so that means that n1 and n2 are kind of small, and also that p is kind of special. So in the parameters that suggest, n1 is 2 to the big and 2 is 3 to the big. So this is kind of a Mersenne-like prime, and in other contexts, this is not something that you'd like to go for. And well, as far as I know, this doesn't lead to any weakness, but I would be cautious about it. I already mentioned that right there. P over 12 supersingular invariant, whereas for n1 you just have roughly square root of p choices. So again, that introduces some potential weakness. In fact, that makes some attack more efficient. And finally, and that will be relevant for the last part of this talk, there is some extra information provided. Remember, to complete the key exchange, Alice and Bob had to reveal the image of PA and, well, for Bob, the image of PA and QA through phi b. Okay? So essentially, as you can do linear combination, they reveal the image of the whole NA torsion via phi b. Okay? So this also could potentially introduce some weakness, although prior to this work, I mean, nothing was known in that direction. Okay, so the point 2 was kind of known to introduce some weakness, and they chose the parameters according to that. Point 1, I'm not sure this actually make this actually lead to any weakness, but that's something I would actually look later. I think it's worth investigating, and now we're coming to that point here. Okay, any questions so far? All right. Okay, so an attack on the key exchange could solve the following problem. Compute an isogeny, so given E0 and E1, compute an isogeny between them of degree n1, given the action of this isogeny on this torsion group. Okay, so natural question is, how useful is this additional information, right? Well, clearly, if n1 equal to n2, then essentially this action should reveal the kernel, right? So if n1 is equal to n2, this would be very damaging to the protocol, and that's why they have this requirement that GCD of n1 and n2 are coprime, is equal to 1. And similarly, if they're not equal but have a non-trivial GCD, then you also able to recover part of phi 1. Okay, so they do require n1 and n2 to be coprime, which is good. Another result in this area is the paper we had with Stephen and his student in TesoCrypt, is that if you have, it's an active attack. So in that paper, what we showed is that in the context where one of the secret key is static, doesn't change, an attacker can not follow the protocol. Instead of sending the right information like phi b of PA and phi b of QA, send some other points, and from this other points that you would send, eventually recover the secret. Okay, so there exists this kind of active attacks where you're not following the protocol, and through several rounds of interaction with the other party, you actually recover the secret key. But what about passive attacks? What about attacks that, first of all, don't require a lot of interaction and just maybe observe one round of the protocol and derive the secret key from there? Okay, so that's the point of this section. All right. So before going into this problem, I want to kind of warm up and consider a potentially easier problem. And here it is. So let's P be a prime and E a supersingularity curve over Fp square. Let phi be an endomorphism of E, non-scalar, a non-scalar endomorphism of E. And I assume that phi is smooth order n1. Okay. Let n2 be another smooth integer such that it's coprime to n1. And let PQ be a basis for E of n2. So we're essentially in a setting of the key exchange, except that phi is not an isogeny between two curves, it's an endomorphism of one curve. Okay? Let's R be a subring of this endomorphism ring, such that that is either easy to compute or given in some way. Okay? So for example, you know the scalar multiplications, right? Given the curve, you know that there are all the scalar multiplications, so that could be an example of R. Or in some other context, perhaps the curve is defined over Fp, and you know both the scalar multiplication and the Frobenius, so you have the whole subring generated by the Frobenius and scalar multiplication. Okay, so this totally realistic assumption. And then the problem I want to consider here is, so given this curve, the basis for E of n2, well, I could recompute that. But crucially, given the image of phi of p and phi of q, the degree of phi and the subring compute phi. Okay? So again, kind of the setting of the key exchange, except that it's an endomorphism ring instead of being an isogeny. So if you look at it from the point of view of what was known before, the best algorithm is essentially this meet in the middle strategy. So the endomorphism has degree n1. So if you take and n1 is smooth, so you could do like square root of n1 in that direction, square root of n1 in that direction, and the total cost is roughly this, and then you get an endomorphism. All right. What I've shown now is a square root improvement to that. So essentially a fourth root of n1 attack, using crucially the extra information that is provided by phi of p and phi of q, the kind of extra information that's also provided in the key exchange protocol. All right. Any questions so far? Okay, so let's go for it. So we know phi on the n2 torsion. Okay. So we can deduce also phi hat on the n2 torsion, right? Just because phi is phi times phi hat is equal to n2, and to n1, and n1 is coprime to n2. So we deduce phi hat on the whole n2 torsion. Okay. Then we deduce the trace of phi modulo n2, right? Because it's just phi plus phi hat. And we also know that the trace is an integer smaller than 2 squares of n1. So assuming n2 is bigger than 2 squares of n1, which by the way is the case in the key exchange protocol, then this information actually gives you the trace of phi over the integers. All right? Let me know if there's any question. All right, so now we will consider this endomorphism, and I want to stress I don't know psi, but psi will be formally a linear combination of phi and scalar integer and scalar multiplication. Okay, so psi. So let a and b be two integers, and let's psi be equal to a phi plus b. I claim that we can evaluate psi on the n2 torsion. Okay, we don't know psi, but nevertheless we can evaluate it on the n2 torsion, right? Because we know the scalar multiplication and we know phi on the n2 torsion. All right, happy so far? The first step in the attack will be to find two integers, a and b, such that the degree of psi, that you can rewrite it in this way, forget about it for now, is equal to n2 times n1 dash. Okay, so n2 is the integer where you know where you can evaluate psi, and well, phi and psi. And n1 dash, you want it to be small and smooth. All right? So my goal here is to find two integers a and b such that the degree of psi is equal to this, such that n1 dash is small and smooth. Okay, and if you look at this equation, degree of psi, you can rewrite it in this form. So it's just psi times psi hat. So a squared degree of phi plus b squared plus ab trace of phi. And we know degree of phi, and now we know trace of phi. Okay, so we know everything here. So we have a quadratic equation, a quadratic Diffie-Hellman equation to solve. Kind of. So this is not given, but we want a small solution here. Okay, I'll come back to how to find a and b in the next slide. But to continue, so we have degree of psi equal to n2 times n1 dash. So I can write my isogeny or my endomorphism phi as a composition of two isogenies, one of degree n2 and one of degree n1 dash. All right? And remember, I can evaluate psi on the n2 torsion. So I can actually identify the part of the kernel of psi that corresponds to the n2 torsion. So I can by evaluating psi on the n2 torsion, I recover the kernel of psi n2, and therefore I also deduce psi of n2. Okay, so now I've computed this isogeny psi of n2, and I've reached another curve, and I know that this other curve, what's happening? Oh no, okay, just give me a second. And I know that this other curve is connected to my curve via an isogeny of degree n1 dash, right? Where is this? I think so. No, it doesn't fit here.
I got one.
So, okay. So you've recovered psi n2, and then for the last part, for this part, as long as n1 dash is smooth and small enough, then you can just apply this meet in the middle strategy. Okay. So what actually I show in the paper is that I can hope to have n1 dash roughly square root of n1, and that leads to the square root improvement I was talking about. All right. So once you get psi of n1 dash, you're not entirely done. So what you do is, well, essentially you have an expression for psi, and you can now evaluate this expression for psi on the n1 torsion. And therefore, you can evaluate psi minus b over a on the n1 torsion, recover the kernel of phi, and deduce phi, and you're done. Any questions so far? No? Okay, so the only thing that remains is this part, right? So we have an equation of this form where the degree is known, the trace is known, and 2 is fixed, and I want to find a and b such that n1 dash is as small as smooth as possible. Okay. Okay. So the paper I solved that by looking at the equation modulo n2. Okay. So modulo n2 set of solutions form a two-dimensional lattice. Okay. And this is quadratic form corresponding to the two-dimensional lattice. So so you can compute this lattice. You can compute a short basis for this lattice. And then you can run some kind of exhaustive search among a small linear combination of this small basis until you hit a vector that has a norm a short norm such that n1 dash is smooth enough. Okay, so you have to kind of balance stuff there, but what we argue in the paper is that you can expect that n1 dash will be as small as square root of n1 by kind of Gaussian heuristic argument, square root of n1, yeah, and that's it. Okay. So what this shows is that in this particular problem, which is a bit similar to the key exchange, when you reveal the image of a large torsion group, this is not innocent, right? This actually leads to a near square root speed up to the problem. Well, some parameter restriction apply, but I think nevertheless it's interesting. Any questions so far?
So all lattice computation is all efficient.
Yeah, it's a two-dimensional lattice, so you can, it's Euclid algorithm. Pretty efficient, yeah. The stuff that is not that efficient is to find a short element in this lattice, right? So a short element is efficient, but finding an element such that n1 dash is going to be smooth. So you expect n1 dash to be, for the smallest vector, to be roughly square root of n1, and then you also want it to be smooth in order. And so if you expect that elements in the lattice have norms that are distributed like random numbers, and if you pay a sub-exponential price to get norms that are sub-exponential size, such that n1 dash is sub-exponentially smooth, then you get the square root speed up, roughly. Okay, but there are all sorts of trade-offs where you can just do a little more, oh, okay, I didn't plug it. You can do a little bit less work on finding short vectors, and then you have to do a little more work on this meet in the middle strategy. Okay, any questions so far? Great. So I guess you guys in particular are particularly interested in the key exchange protocol. Oh, I thought I had removed that. Well, it's okay. Essentially, it's an open problem in the paper, but I think it's now solved, so I wanted to remove it. The case of, just to say a word about it, the case of where the curve is defined over Fp. So now you know a bit more than just the scalar multiplication, and you could hope that, well, this equation here, you could hope that n1 dash, you can choose n1 dash a bit smaller. The way I think, well, the kind of idea we have to solve it actually doesn't involve solving this equation, but I think there should be a polynomial time algorithm in this case. Anyway. Yeah. Okay, so this is what you will be interested in. Now we're back to the kind of key exchange setting. So let P be a prime, and 1 and 2 be two coprime integers. E0 supersingular P curve over Fp squared. Phi is an isogeny between E0 and E1 of degree n1. I assume that I know two subrings of both E0 and E1, of both the endomorphism ring of E0 and E1. And well, whereas in the previous attack I could just choose the scalar multiplication, so as generic as you would like. Here I have to assume a bit more about R0. So if R0 is just a scalar multiplication, at the moment I haven't found a way to make these techniques work. So I need to assume that I know a little bit more than that. But you'll see it makes sense in some settings. And the problem here is, so given all those parameters, and given the image of phi on the wall and two torsion compute phi. Okay, so kind of a key exchange setting. And again, if you don't use this information at all, like people did in their previous analysis, then the best algorithm is kind of meet in the middle, and that's called square root of n1. Okay, so I'm interested to see whether those techniques can actually lead to interesting speed up in that case as well. All right. Maybe I should say a word about this assumption here. So in some implementation work, including by Microsoft people, the curve E0 is chosen as j equal to 1728 for efficiency reason. And in that case, you don't just know the scalar multiplication, but you actually know the whole endomorphism ring. Okay, so the assumption is realistic in that sense. Okay, any questions so far? General ID. Let theta be an element in the endomorphism ring of E0 that is non-scalar. Sorry, should have written that. So we consider the endomorphism of E1 given by the composition of phi1 hat, theta, and phi1. Okay, I don't know this, right? That's about what I want to compute, but I know I can evaluate phi1 on the N2 torsion, and I know theta. So even though I don't know phi, I can actually evaluate it on the N2 torsion by what is given in the problem. Okay? And then I have an endomorphism of E1 where I know its image on a big torsion group, and I can apply the techniques from the previous section on this. Okay? Once I've done that, I've kind of recovered phi. But phi is not what I want. I want phi1, right? So to compute phi1, I kind of intersect the kernel phi with the N1 torsion. This gives me more or less the kernel of phi1 hat, sorry. And then I compute phi1 hat, and then I use phi1 as well, and I'm done. Right? I've kind of hidden some aspects here. There are conditions on the parameters. N2 has to be big enough compared to N1 for this to work, etc. I'll come to that now in a little bit more detail. But the intuition is, I mean, the general idea is here in this slide. So a couple of remarks. Several authors, including people sitting there, have been using J equal to 1728, just because that makes computation more efficient. Okay, so in that case, not only you have a subring of E0 of an endomorphism of E0, but you know it entirely. And not only you know it entirely, but also there are small elements in this one, right? There is a degree 1 non-scalar element in the endomorphism ring. And both aspects, the fact that you know the whole endomorphism ring and the fact that there are small elements, are useful in this for these techniques. Okay? So in the paper, what we do is we develop 2 attacks that follow kind of those lines. But I don't think that this is the end of the story. So, well, I already mentioned some improvement to come, and I expect more to come. All right. So just to say a few words about this. So if you take E0 equal to 1728, and if you have this parameters, so N1 roughly the size of p squared, which is what you'd like if you want the 2 curves to be uniformly, if you want the second curve to be uniformly distributed, you would actually need N1 to be roughly equal to p squared. So that's what you would like. But also for the attack to work, you need N2 to be a bit bigger than that. Okay, so those are the 2 conditions for this attack to work. But under those 2 conditions, you actually get polynomial time key recovery. Okay, following those lines. Another variant that we develop is only assuming that this guy has a small element, so I don't necessarily require to know all of it, but just I need it to have a small element. And I'm given a bit less information, so I have to be a bit, I have to require a bit more from that side. So the requirement here is that log N2 is roughly square root of log N1. So it's the balance between N2 and N1 is quite different. Right? N2 is quite significantly bigger than N1 in this case. In this case, it's just 4 times as large in bit size. Then in this setting, we develop another attack. It's more, it's a variant of the above strategy. It's a recursive recursive attack where we take the problem and then reduce it to another problem of the same nature but smaller parameters. And this leads to, again, a polynomial time key recovery attack. As I said already, I don't think this is the end of the story. I mean, you could obviously balance parameters differently if you are not just interested in polynomial time key recovery, but just want to look at maybe some still exponential but more efficient than previously, etc. So I think there's still a lot of work to be done in that direction. On the other hand, to the best of my knowledge, and of course I tried a bit, if you take the parameters as suggested in De Feo Jao-de Feo paper, there you have n1 and n2 roughly equal, and I haven't been able to develop an attack following those lines yet. Okay, but it's plausible that it will come. I don't know. Any questions so far? Yes?
Like, is there a middle ground here? Like, if it's 4 times as large as polynomial, and if it's about equal, nothing happens. Like, what if it's twice the size?
Yeah, you expect trade-offs.
Yeah, right.
Mm-hmm. Yeah.
And with the size of these n1 and n2, so then I'm guessing that you'd need these isogenies not to be rational over fp squared.
Why?
Well,
Oh yeah, that's true. Well, no, the isogenies are always over fp squared, but the subgroups, the torsion might be defined over extension fields, but the isogenies are always defined. I mean, you can for supersingular curves, you can always define the isogenies over fp squared. So this attack only applies to kind of my variant, if you like, or whereas this one applies to both. Assuming that, I mean, there's one reason you might want unbalanced parameters. So suppose you're in a setting where one key is static and corresponds to a server, perhaps, then you would like to put more security on the static key. Okay, so in that case, it would make sense to have n2 bigger than n1, perhaps, or the other way around. So I think I phrase it in the abstract as this leads to attack of variance in a plausible attack scenario, and I think that's an accurate description. It doesn't yet break the key exchange protocol for the parameters suggested, but watch out for further results, and if this paper hasn't come, it would have been plausible, perhaps, that somebody would have tried unbalanced parameters to put more security on the static key. Right? I'm glad you don't disagree on that. Okay, any questions so far? Okay, so to conclude, well, we can build some cool crypto based on isogeny problems and recycle elliptic curve cryptography in a post-quantum world, which is kind of cool. So there are problems there, and I think they're very interesting. But betting or I wouldn't put national security on relying on that, right? I mean, it needs further study, even though I think the situation is better than other problems that are currently suggested for post-quantum security, in the sense that this had been studied before it was suggested for crypto. At least if you really focus on the endomorphism ring computation problem, don't go for variance like in the key exchange. But nevertheless, I mean, it's interesting problems that do require definitely more work on cryptanalysis before we trust them. But I hope there will be a submission to NIST because that would motivate more work in that direction. Really, and who knows, if in 10 years' time these attacks are still the best attacks, then it makes sense to actually put some valuable data in the hands of those problems. And then last point I want to make is this one, which I think is I wouldn't say it's a shock to people, but certainly it wasn't known before. Personally, I think it's kind of natural, right? You had the problem where you reveal additional information. Of course, this information wasn't used before, but it was always kind of natural that it was a potential weakness in the protocol, and the algorithm I presented go in that direction. All right. Any questions? Yes.
Which of the post-quantum schemes would you use for national security?
No, I wouldn't. I think all of them need more study, and
I agree.
and even lattices. I mean, for the parameters suggested, I don't think there has been much cryptanalysis work, and I think this. I really hope there will be a submission in that, because that will motivate more work as well. I don't know. Are you planning to make one? Yes, great. Will you use J equal to 1728? Maybe.
It's kind of difficult to come up with an alternative.
That's true. I should have mentioned that. If you, it's not known how to generate a random supersingular J invariant, if not by taking a spatial curve and then making a random walk. So you could do that, but then those attacks kind of, there's a risk that they come back in kind of a backdoor way, right?
Someone still knows the walk to the
Yeah.
subfield curve. Then.
Yeah. So in a sense, the impact may be even bigger. But yeah, I wouldn't recommend using J equal to a special J though. But yeah. But on the other hand, you will pay a price in efficiency or in the setup if you don't.
Or just that, if there's a reasonable way to come up with a different J, where someone doesn't know the walk to the J equals 1728 curve.
Yeah, I've thought about it. Haven't found anything.
When you can do CM to get a non-subfield curve, but you
It's the
still
same.
know the
If CM is efficient, that means the discriminant is small, and then you can find a small degree of isogeny, endomorphism. So essentially, it's the same setting.
Exactly.
I don't see any way around it. So you'll be using J equal to 127 because you care about efficiency more than security. Yeah.
It's already the slowest proposal.
So how does it compare? I'm curious. So how would you compare it in terms of efficiency with other protocols? How will you sell it? Like why is this the best one?
Just a different problem, right? And it has small keys.
Small keys. So
it has the smallest keys, but it's the slowest probably.
Is the slowest one?
By orders of magnitude.
Orders of magnitude.
Yeah.
Really? Wow.
But it might be fine, right? For some applications.
So how fast is it? How long does it take to make a key exchange, more or less?
It's about 10 milliseconds in a modern Intel computer.
So you didn't notice it on your browser, would you?
Yeah. Depending on the application, it wouldn't be a problem. So that's why it's interesting. And also, people like elliptic curves, and this is related. So
Yeah. Well, it's kind of trendy at the moment, which is good for me. Other questions?
So let's thank Christophe again.
Thank you. Oh.